Hello everyone, and welcome to the first lecture video in the Class 10 series of lecture videos. In this series of lecture videos, we're going to introduce the concept of stereochemistry, and we'll see how far we get with it for the Class 10 time. So, this is Chapter 5 material. We've covered the first 4 chapters, and now we're launching into kind of a complicated subject, and you'll see that there are a lot of definitions. I don't know if they give language credit for organic chemistry classes, but they probably should. So a good chunk of this course, or this part of the course, will be in learning the definitions and really understanding them and how to apply them. So let's start with something we've seen before. These are the 2 staggered conformations of butane. Conformation 1 is in the anti form, and conformation 2 is in the gauche form. And we could ask the question, are these stereoisomers? Well, technically, due to the definition of what stereoisomers are, we can say yes. Of course, they can interconvert by rotation. So there's free rotation around the C2-C3 carbon-carbon bond in butane, and so conformations 1 and 2 can interconvert with each other. So you can't really hold either of those conformations still to have a set of stereoisomers. So that begs the question, what are stereoisomers? Well, stereoisomers are molecules whose atoms have the same connectivity, but whose atoms have a different orientation in space. So you've got 2 molecules, they have the same number and type of atoms with the same connectivity. So they're connected in the same way. However, for those 2 molecules, the atoms have a different orientation in space. Just by that definition, could we call the different conformers of 1-bromo cyclohexane stereoisomers? And yes, again, the different chair conformations 3 and 4, with the bromine either equatorial or axial, are indeed stereoisomers. But again, they're in a rapid static equilibrium, so they interconvert with each other to get to some sort of percentage at equilibrium. So 1 and 2 and 3 and 4 are pairs of stereoisomers. They have different energies. This is not always the case for various pairs of stereoisomers. So let's launch into consideration of some stereoisomers and some more definitions that'll help us in this course. So enantiomers, there's a big $10 word. That's a pair of molecules that are non-superimposable mirror images. Okay, so here we go. Here's a chlorinated, brominated ethane molecule. So we have 1-bromo, 1-chloroethane. This is a stereoisomer, and so if we look at its mirror image, we can draw a pretend mirror plane in the plane of the page, and this is what it would see if it were looking at itself in the mirror. So the next question we ask is this the same molecule as this particular stereoisomer of 1-bromo, 1-chloroethane? And so if it's the same molecule, there would be some way where we could reorient this molecule such that all the atoms and all the groups would be able to overlap. You can sort of see, if you try to flip this around and superimpose the methyl and the hydrogen, there's a problem. The chlorine will be pointed forward, and the bromine will get the dash bond, so those will not be able to superimpose. So in answer to the question, can you superimpose the above two molecules on each other by rotation? And the answer is no. So enantiomers have the same physical properties except for two. So they're identical in boiling point, melting point, retention time on silica gel, energies. They have all these similar physical properties except for two, and those two properties are the way they rotate plane polarized light and the way they might interact with other things that are chiral. So there's another definition that we will be encountering soon. A chiral molecule or object has a non-superimposable mirror image. Of course, we'll see that a little later. So, next question. Are these two molecules non-superimposable? So this version of 2-chlorobutane is indeed a different molecule than its mirror image. Because there's no way you could turn its mirror image such that you could get all four groups on this coming off that carbon to superimpose. And what am I talking about? I'm talking about an ethyl group, a methyl group, a hydrogen, and a chlorine. So if you turn this around and try to superimpose the methyl and ethyl groups, the hydrogens and the chlorines would not. So these are a pair of enantiomers because they are non-superimposable mirror images. How about this 3-bromopentane? Is this non-superimposable? Well, it might look non-superimposable, but here's the deal. You can rotate freely around carbon-carbon single bonds without breaking bonds or changing fundamentally, taking apart and reorganizing, forming new bonds in this molecule. So if you rotate around a couple of these carbon-carbon single bonds, you can get to the exact same identical molecule. You can now superimpose all the groups of this molecule with the molecule that we started out with. So we say no. And again, we reach that conclusion through rotation of two carbon-carbon single bonds, which we're allowed to. And we arrived at a superimposable image. So these are not enantiomers. In fact, they are identical. And indeed, we would call this compound achiral. And we'll get to that definition here soon. Achiral molecules do not have non-superimposable mirror images. So, how about this pair of molecules? Are they non-superimposable? And the answer is yes, they are non-superimposable, and they are mirror images, so we have to define them as enantiomers. They are not the same molecules. So I know this is complicated. It takes a little bit of practice. It probably will help if you have a molecular modeling kit. So sometimes even tetraalkyl ammonium cations can be non-superimposable. We'll take this one, for example, where we have a nitrogen bonded to a methyl, ethyl, isopropyl, and propyl group. And indeed, its mirror image is non-superimposable. So all molecules that have non-superimposable mirror images are chiral. That's a definition. Chiral molecules and objects are indeed non-superimposable with their mirror images. If mirror images are superimposable, then the molecules or objects are achiral, so they are without chirality. So those are important definitions. One can, do some tests again. So How about this 2-methylbutane? Is it chiral or not? Well, 2-methylbutane again is achiral due to free rotation. And so in the next video, we'll look at a couple of easy ways to tell if molecules are chiral or not with a few simple tests. And hopefully that will, relieve the stress for the majority of examples you might encounter.